Hi everyone, in this video we're gonna discuss what FlashAttention is, how it works, and also we'll look at my personal implementation on Triton of FlashAttention 2, and we're gonna compare this with existing solutions from Tri Dao, PyTorch, and OpenAI. But before this, I want to introduce my free ML course about classical ML algorithms. This course is called ML Algorithms from Scratch, and this is how it looks like. So this is repository on GitHub. So it has a short description. So here you see the current content. It consists of some theory about metrics and optimization methods. Then it has supervised learning algorithms, unsupervised learning algorithms, and some additional resources. So sometimes you may have problems with GitHub. I mean, opening IPAN-B files, or to be short, Jupyter notebooks on GitHub. So in this case, you can use Kaggle. So because on Kaggle, these notebooks also exist. For example, we can open KNN algorithm. So this is just an example to show you how this course looks like, the structure of one tutorial. So it has short description, some schemes, then principle of KNN operation, formulas, its optimizations, variations, then Python implementation for Scratch code, so with normal naming, and this will be very useful for beginners. Then we can see that we use the real data sets, in this case Iris dataset, with with the results of this dataset. Also it has some conclusions and examples how to train model, our from scratch models and scikit-learn, and plots with the results of our algorithm. So, and also at the end it has pros and cons and also additional sources. So, and all algorithms have the same structure. So I'm gonna show you how this looks like in Kaggle with other files, for example, all popular algorithms from scratch. So the structure is the same like on GitHub. So all the links you can find down below. So, but now we're gonna start with FlashAttention. So I decided to create this paper with name like Accelerate LM to the Maximum, how I created a cross-platform FlashAttention with support for Turing Plus architectures and more. So here we have a long read paper tutorial, and I want to start with this. So we both know that now transformers rule the high bell in the world of machine learning. So it has become possible with such products like ChatGPT and the same language models. But the main thing which lies under transformers, this is attention mechanism. This is a very cool thing because it lets to catch the long context. It helps models to understand almost everything with a good quality, and so this mechanism is cool, but it has one problem. This is very slow, and also it consumes a lot of memory. So in this case, there are some improvements of this concept. One of them is called FlashAttention. It was developed by Tri Dao and his team, And also some companies like or products or frameworks like PyTorch or OpenAI, they decided to create their own implementations, but all of them have some, I would say, some huge cons. And that's why I decided to implement my personal algorithm of FlashAttention 2 on Triton with support for Linux and Windows Turing Blackwell architectures. So that means that you can work in Kaggle and Google Colab. Also, it supports homo and heterogeneous clusters, and it has optional determinism and also ability to manually customize kernels. And now we're gonna discuss how it was implemented, what it is, how it works. I think this will be very useful. But before this, I want to start from such thing like research engineering. So you both know that there are ML engineers who use prepared models or algorithms, for example, like frameworks like scikit-learn, PyTorch, or a lot of you, I'm sure, like to use Hugging Face or LangChain. But how it was created? There are ML researchers, they develop on the paper the concepts, they create the concept. And there are ML engineers who use this, but there is the intermediate specialist who can link both of them. So such specialists take research papers and transform them into real working code, production code. And this is my direction. And I had the real problem when I needed to use older GPU architectures like Turing, and I decided to create my personal implementation because there is no any existing implementation which will let you to work with all GPUs. So also there were some additional reasons why I needed to create this. It was the real project to accelerate LLM, but now I want to start with GPU, what it is, and why we need to know the main components. Okay, let's start. So GPU, as you know, is used to train language models and neural networks in general. It has become possible because GPU lets you to parallelize on a lot of cores, almost any task. So in the term of ML, that means that we can easily parallelize computations. So I mean that these computations are simple, these operations are simple, and GPUs are made, well, I would say well made for this task. So not only for graphics. And before to deep dive in FlashAttention concept, I'd like to show you the main components of a GPU because this is very important to understand the next material. So let's start with performance indicators. FLOPs, floating point operations per second. I will read this. Theoretically, the maximum number of floating point operations performed per second. For example, if this indicator is 10 teraflops, then up to 10 trillion operations per second can be performed on GPU. The next thing is memory bandwidth, the amount of data for read-write operations for varying GPU memory levels per unit of time. Latency, the time from requesting to receiving data from various GPU memory levels. Also, I forgot to say that this description uses example of a factory to understand it more better or more simpler. So the next thing is streaming multiprocessors. This is our factory workshops because this thing also you need to know in FlashAttention, and you'll understand a little later why. So each streaming multiprocessor is an autonomous production model which contains the next things: CUDA cores, universal machines for basic operation, tensor cores, specialized pipelines for ultra-fast operations, and SRAM, the most important things, and registers. But we'll discuss it a little later. The next thing, executors and schedulers. Thread, a single worker performing elementary operations, warps. These are brigades or groups of threads, usually this is 32, to perform identical operations on different data. And the interesting thing that any delay stops the entire group, for example, like waiting for data. So warp schedulers, you can look at these like dispatchers who distribute tasks between warps across CUDA cores to minimize their downtime. Okay, now we'll look at the most important thing for this topic, and this is memory hierarchy or warehouse system. So HBM, high bandwidth memory. So this is the main storage. It consists of a lot of gigabytes on modern GPUs. So this is good for some tasks, but it has a very low bandwidth relatively to SRAM, static random random access memory. So, and SRAM is a local buffer inside each stream multiprocessor. It has a small volume between 64 and 256 kilobyte per stream multiprocessor for modern GPUs, but it has also extremely high throughput, near 20 terabytes per second. And starting with Volta architecture, this is the single physical block that consists of two parts. L1 cache automatically reduces data access delays to L2 and HBM shared memory. And this is the most important thing for FlashAttention. This is used for explicit data to exchange between threads. And this is a programmable memory, so we can use it for our tasks. What that means. So also there is such a thing like L2 cache. This is something intermediate between HBM and SRAM. This is used to reduce the number of requests so its volume is several tens of megabytes. And the last thing is ultra-fast memory. This is called registers. So this is very small memory, and this is unused directly in FlashAttention. So also there is a such thing like kernel. This is programmable software GPU core. So this is a single set of instructions for parallel execution by threads on hardware cores using SIMD. This is a thing like single instruction, multiple threads. And two last things like memory controller. This is this thing which is specialized hardware unit that manages read-write operations for a specific GPU memory segment in such a way as to ensure maximum throughput and minimum latency for it. And modern GPUs have several such controllers, each of which serves its own memory channel in parallel. Okay, also there are such things like PCI, maybe you heard about this, and NVLink. PCI Express is a standard high-speed communication channel between GPU and CPU, and it provides access to system memory and control of GPU operation. So this is a base standard, mandatory for all configurations. And there is additional standard which is called NVLink, and the main difference that it allows multiple GPUs to exchange data directly peer-to-peer, it is called so, bypassing CPU. And this is an optional thing. So these are the main components we need to know before we deep dive in FlashAttention. But before this, we need to also know what the classical or vanilla attention is. And let's start with prerequisites of appearance and is the main drawback. So everything has begun with recurrent neural networks and embeddings. So let's start with embeddings. So embeddings, I will read this, are a set of potential features in the form of trainable vectors necessary for a better description of the relationships between the elements of a sequence in an n-dimensional space. So what it means? So it means that for each word we create a vector which has some elements. This is like features, and these features for this word, for each word, will be different and they will be trainable. So, or how I wrote here in the text version is in the example of a text. That means that a vector representation of tokens, these are words or parts of a text, in the space of their potential features in such a way that the geometric proximity between these vectors reflects the semantic and syntactic proximity of the corresponding words. Maybe it sounds hard, but here it is written that, simply put, embeddings allow tokens of similar meaning to be located closer to each other in the feature space, and different tokens to be located further away. And in addition, embeddings can be positional, and in practice they very often added to token embeddings. So for example, after learning or training, the embeddings of words king and queen will have high geometric proximity since both denote monarchs, but their vectors will differ along a certain dimension, for example, gender. And on practice, it was noticed that operation king minus man plus woman will give a result which is close to vector queen. And another thing why positional embeddings are important, because for example, we can have two sentences and they will have very different sense because of position. For example, the king rules the country, not the queen, and the queen rules the country, not the king. So in reality, this is a very important thing. So, and we need to try to train language models to see this difference. So, but before this, we need to also refresh our understanding what recurrent neural network and its limitations, because it led to appearance of transformers. So RAN, in a very simplest form, looks like this. So we have such scheme where we can see that it has some hidden states where hidden state, this is a compact vector representation of the entire previous sequence. So that means that how it works, we have an input, So we pass this through our hidden layers. We'll get the first output that for the generation, the second output for the second input. We use the previous information from the previous hidden state. And it causes some problems. First of all, loss of context on large sequences. So this need to compress the entire sequence in one vector leads to the loss of information due to its updating at each time step t, which is also known as information bottleneck. Another problem that this is hard to parallelize because of a sequential nature. So there are some partial solutions like parallelization by batch, time blocks, or layers, but these decisions don't solve the problem completely. And the last thing, that the training process is unstable because it leads to explosion decay of gradients. So why it happens? Because during backpropagation through time, the computational graph should be expanded to the Rn using the same parameters at each time step. And in this case, it means that gradient for each parameter should be summed over all the places where this parameter occurs in the deployed network. So, in this case, if the eigenvalues of the matrix of weights of the hidden state are greater or less than 1, this will lead to explosion decay of the gradients, respectively. So, and these problems have become the base or the reason why attention mechanism was appeared. So, and in the first time, it was introduced for machine translation tasks in 2013. So, and how to say more simpler. So the main idea that decoder in RNN has become to have ability to dynamically access various parts of the source sentence at each generation step through the calculation of attention weights. And this will be represented as a weighted sum of encoder states. So, and this idea, so maybe now you don't understand anything, but we will look at this more detailed in several seconds. But this idea lied in the base of creating attention mechanisms. So, and we will look at one example how it works. For example, there is a such sentence: she rose from the bed to smell the rose. So as we can see, rose here in this position means action, but in this position rose means flower. And this meaning of the word rose strongly depends on the context. So in one case, as I said, it means action, in another one a plant, and this context is determined by the connection of one word, for example this word, with other words. And this is the main idea of attention mechanism. We create the matrix, attention matrix, where each word, for example rose, will be connected with other words. So, but this matrix will show connection or link between all words with each other. So the logical and the simplest way at the same time may look like is to use input embeddings directly to determine the semantic proximity of their features through a scalar product. Why scalar product? Because it reflects the alignment of the vectors. So, and in addition, so if we pass these values through a softmax, it can give us a matrix interpretable. So on this matrix we will look at like attention weights, which will show that the closer these values to the one, the stronger the connection between words. Or simply put, such matrix will allow the model to find out which words are worth paying more attention when referring to the current word. And if we multiply the result in weights by the initial embeddings, it may give us the new representation of tokens or words, which will contain all information from the context. We can describe this mathematically like this. I mean that now I have described the intuition of appearing of attention mechanism, and you can compare this with the original formula, and this will be different because this approach we described now, it was intuitive. So this is the intuitive or logical appearance of attention mechanism to understand how people came to this, how it works. But this variation has some drawbacks. First of all, embeddings are primarily designed in their purview to highlight features in a word due to their static nature. So that means that they won't be able to properly separate its meaning dependent on the context. Simply put, the feature space in the feature space, rows as an action and rows as a flower will be geometrically close together. And that means that they will have a similar meaning. Only because the embeddings don't know how to separate this very meaning in the context. Another thing that the matrix of attention weights obtained in this way will be symmetrical, which means that it's enabled to determine the direction between words. For example, she smells the rose and the rose smells her will be the same for the model if we use this approach, but these things are different. So that means that this matrix should be asymmetric. So it should show which word I think more simpler. So it will show which word is object and which word is subject. Okay. So, and if this approach with embeddings in their pure form cannot solve these problems, we need to try to train these embeddings to perform these tasks, and this has become possible with using linear transformations. So that means that it is enough to use linear projections with different weight matrices WQ and WK, which will allow us to project the initial embeddings into different subspaces Q and K. And as the result, attention scores become context-dependent and asymmetric. And also, for stabilizing training, the dot product of Q and K is additional scaled by square root of dk, because it allows to keep variance of the output values within one. And at the end, we can see this formula, and this formula is from the original paper, so this is why these metrics are used. And now We need only to add another linear transformation for the initial embeddings with the weight matrix WV in order to project them into the subspace V, which will enhance relevant embeddings and suppress irrelevant ones, depending on the context determined by the attention matrix. And in the end, we'll get contextualized embeddings where each token will be represented with information taking into account the entire context of the sequence. So, and this formula looks like this. So, if to be more simpler, so we use linear projections or linear transformations to project our embeddings in different subspaces, thus to separate meaning of a word depending on the context. For example, just imagine that we have x, y axis and xy axis, for example here, okay, and here will be one word and here will be another word. Meaning of one word, for example, rose, action, and flower, they will be located closely. But after transformations, we can transform space, for example, like this, and one meaning will be here, another one will be there. So, and this is the main reason why we use linear transformations. So, and then using this attention metrics, we can get at the end contextualized embeddings by multiplying these weights on the initial embeddings. So maybe you heard such analogy that QKV matrices are query K value, and this is linked with a search query database, but this is wrong explanation. So this example is wrong, and these names have more historical character in terms of neural networks. So in reality, so these are just three trainable linear projections which were designed for specific tasks, and that's all. So also in practice, very usually, I would say almost always, we apply a causal mask M. This is a matrix where minus infinity is below the main diagonal and 0 is located on it and above in front of softmax. This approach guarantees that zero weights for future positions in the sequence. So, simply put, this approach or this matrix will not allow the model to look at the future tokens. This approach helps to avoid overfitting. So, and this idea with this attention mechanism in practice also expanded with applying H separate predictions in parallel for each attention function. And this mechanism is called multi-head attention, and this approach allows model to make a better focus on various aspects in data. So that means that each head will be focused on learning its own prediction. So this formula looks like, and there is an interesting scheme from the illustrated transformer paper. So it looks like this. For example, we have the word eat and we see the connection this word with other words, and each color describes each head and its activity. So the darker or the brighter the color, So the more active, the more, the more active connection this word with another word in using several attention heads. So I mean that each attention head can find some different aspects, and it will show how these aspects impact on the connection in general. Okay, so the next thing that this mechanism has some drawbacks. Yes, it looks very well because because it has connection each word with other words in a sequence, but there are some drawbacks. And this drawback is linked with the quadratic complexity. So you can see this here, O n squared d in time, O n squared by peak memory consumption. So, and maybe sigma, or sorry, I forgot this symbol, and its complexity is nd plus n squared by IO complexity, the number of read and write operations between different memory levels. So, and this is the reason why FlashAttention was created. So this approach is amazing. So, but before to start with this, so also I want to mention that there are also some another approaches, but they're linked, let's say, with approximation. So that means that these methods are approximate, and they're called like linformer, performer, and reformer. So, and their general idea is the same, and it tells us that we need to sacrifice accuracy to get linear complexity. And yes, so actually these methods can reach O and D and O and log n difficulties, but it has serious compromises. That approximation errors were introduced, and it affects on the quality of the models. And we need to change architecture of attention mechanism, and also it can lead to overfitting of the models. So, and also this approach often didn't scale well on different types of data. So, and there is another idea. There is exact approach. So, and instead of changing the mathematics of the algorithm, we can optimize its implementation for modern GPUs, because the key insight came from a deep analysis of vanilla attention's performance profile. So let's start with FlashAttention 1. So in the work of Tri Dao 2022, it was found that vanilla attention is limited not so much by computing resources as by memory access operations, namely multiple access to HBM slow memory. So for simplicity, HBM slow memory, SRAM is a fast memory. So, and we have some number of such operations, these operations, and the authors of this paper propose the new approach, which reduces the number of read-write operations, these operations, to slow memory without approximating results. It has become possible by organizing calculations in such a way that the intermediate matrices S and P are stored in RAM, and only the final result or attention output is recorded to HBM. And this algorithm contains three fundamental principles. Kernel fusion, we can see this work here. So instead of doing these operations separately, we can combine this in one superkernel. So that means that all the basic operations during the calculation will be combined in a single superkernel, as I said before, completely emulating intermediate calls to HBM and multiple kernel launches. So this process is automatic. Another thing is styling. This is the technique when we split our data, in this case QKV matrices, on blocks. Usually blocks is chosen as 2 of power n. In practice, this is in a range between 64 and 512. So this size depends on its RAM size. The higher RAM size you have, the larger blocks you can use. So how it works? We split data on blocks. These blocks we compute in fast memory, and then we upload results into slow memory, HBM. Another thing is softmax. Instead of calculating softmax for all attention metrics, we calculate softmax for each block. So for the current block, we take the current block, we compute this, and we calculate softmax for this block. Formulas looks like this, and schematically it looks the next way. So everything is simple, and this idea is amazing. Another thing is linked with the backward pass. In standard attention mechanism, it looks like this. So, but in the case of FlashAttention, we don't need to store intermediate matrices S and P to calculate gradients. Instead of this, these matrices can be recalculated, and this way can let us to reduce peak memory consumption to ON. And in addition, that this way can let us to save memory in 10 or 20 times depending on the sequence length. It also speed up the algorithm into maybe between 2 and 4 times. And in general, we also can extend this idea to block sparse attention. The idea that we use structural sparsity at the block level, which significantly reduces storage and computing costs for long context. So what it means? It means that we don't materialize the full matrix. Instead of this, we mark the most preferred blocks. With 1, it means we need to calculate them, and 0, we need to skip this. And at the moment, this is the most fast algorithm of all existing approximate methods in attention. So also authors of this technique have made some experiments. They used 8 GPUs A100, and they got the next result. You can stop and read here. So, but the main idea that it led to speed up training GPT in 3 times. It took less than 3 days to train GPT small instead of almost 10 days. And for GPT-2 medium, it took 7 days instead of 21. So this is amazing. So in practice, that means that we can use less GPUs to get the same results. So what I mean, for example, the whole training process for GPT-2, as I said before, 21 days, and we can use in 3 times less GPUs to get the same result with FlashAttention. So that means that we don't need to use 800 GPUs. Instead of this, we can use only 3. But as practice showed, this technique can be even better. So, and let's look at the FlashAttention 2. And the next work, Tri Dao 2023 performance analysis show that FlashAttention is still far from as effective as low-level primitives like optimized metric multiplications, GAM. So it reaches in forward pass only 30% of theoretical maximum flops. And for backward pass, this is 25-35%, while GAM shows 90 and 80%. And this is linked with suboptimal distribution of work between different blocks of threads and warps on GPU. And to solve this problem, developers of this technique offered some improvements. The first one is updated online softmax. This is aimed to reduce the number of non-matrix multiplications operations or non-matmul flops. And it has become possible with 2 tricks. The first one that we use delayed scaling of the output accumulator, and it looks like this. Another thing that we can save more memory with backward pass, because instead of saving maximum and sums of exponents separately, we can do this in one combined tensor. So this looks like this, and the whole algorithm for improved online softmax or stable online softmax you can see here. So we can stop the video, we can read this, everything simple and cool. And the next thing that it was added the additional parallelism in the length of sequence. In forward pass, this is achieved through an external loop along the length of sequence where each block of data queue will be executed independently in this thread block. But for backward pass is used parallelization along the length of the sequence in the outer loop, but not blocks of queue rows as in forward. So it uses blocks of K and V columns, each of which will be executed independently in this block. Also, to eliminate the race condition, the atomic operations like atomic add are used. So scheme is represented here. So also we need to keep in mind that using atomic operation don't guarantee the order of operations, and that means that if we use atomic operations, our algorithm won't be deterministic. It means that if we want to get the reproducible results using any random seed, I mean that we run our algorithm the first time, then we do this the second time, and if you want to see the same results, atomic operations don't provide this. Instead of this, we need to add additional mode optionally, where it will be processed sequentially. I mean this row. If determinism is necessary, this mode should be made optional by adding sequential processing of KV columns blocks. So, but also we should keep in mind that it will decrease the performance by 20 or 10%. It depends on data and your settings and sequence length, of course. And the last thing which is used, this is more efficient work of between warps. This is used to minimize read-write operations in shared memory, and also it is implemented in two places. In forward pass, instead of using the k-split scheme, so that means that when for each block K and V works was distributed among 4 warps, while Q remained available for all warps, it was proposed to divide Q between 4 warps and K and V leave available for all warps. On the scheme, it looks like this. So in FlashAttention 1, we use split K scheme when we divide our data in K and V with thread blocks or warps. So, but in FlashAttention 2, to minimize read-write operations, we do another thing. So, as I said before, K and V will be executed in these warp blocks, and Q will be executed like this as FlashAttention 1, K, and V. Okay. The whole algorithm looks like this for forward pass. So the main idea that we divide QKV into blocks, and we load these blocks sequentially or using parallelization in SRAM. So for backward pass, it looks almost the same, but here we can use atomic operations in the parallel mode, parallelization with sequence length, and it lets us speed up our algorithm, but we should know that, as I said before, the performance may be less on 10 or 20%. And all of these improvements have led to process the sequence length of 16K for the cost as 8K. So what it means, if we take the FlashAttention 1 and process the sequence length in 16K, now for this, I want to say that processing of FlashAttention 1 in 8K will be the same in terms of cost if we use 16K in FlashAttention 2. So it has become twice faster. The next thing, this is FlashAttention 3. So we won't discuss it very deeply, just I wanna say on some things. The first one, that this is almost the same what FlashAttention 2, but this is an adaptation to more modern GPUs architectures, I mean Hopper and Blackwell, because these architecture is different and they have some new options, and if we use these options we can improve almost in 2 times FlashAttention 2 on these GPUs, and this is called FlashAttention 3. here use some techniques. The first one, asynchronous tensor cores and tensor memory accelerator. The second one is overlap of geometries of max operations. There is such a thing like ping-pong scheduling. This is based on synchronization of barriers necessary to force the launch of a single warp group earlier than the other one. And the last thing, that the modern GPUs have an ability to use low precision operations like floating point 8. And this technique has some problems, and to improve this, there are two approaches. One of them block quantization, and the second one incoherent processing. So incoherent processing is used Hadamard transform. So what it means, before quantization, the tensors Q and K are multiplied by random orthogonal matrix, and it allows the outliers to be evenly distributed over all the elements. And in block quantization, instead of using a single scale for the entire tensor, its own scale is calculated for each individual data block, which significantly improves accuracy. So, and as you can see, these techniques are linked with the latest GPUs, and I mean that there is no any sense to apply FlashAttention 3 to Turing or Ampere or Ada architectures. So that's why I decided to use FlashAttention 2, because this is the most universal implementation, so it can work well with all older generations of GPU, and also it works not so bad. It was described in the paper with modern GPUs. I mean that if you compare FlashAttention to on Hopper or Blackwell GPUs, you will get much better results with if we compare this with vanilla attention. Okay, the next thing, why we use Triton and not CUDA. Let's start with the fact that CUDA is a low-level framework from NVIDIA. Yes, this thing is cool, but to use this, we need to know C++, and also we should deep dive in GPU more deeply. I mean that this is hard, it takes more time, it takes more lines of code in serial times. That's why I use CUDA. So CUDA, sorry, not CUDA, Triton. Triton, this is the language. I can say till the end that this is the complete language. I would say that this is like framework from OpenAI, and it lets us to perform low-level operations with the Pythonic style. So you just need to know Python, you can read some documentations, watch tutorials, and you can start writing your own Triton code. So in practice, that means that we can spend between 800 and 1,200 lines of code and send 3 and 5,000. So these numbers have such a range because all depends on the task and the style how you write code. And also this code is much easier to support. So that's why I decided to use Triton, but we should know that Triton is not so widespread thing as CUDA, so it cannot change CUDA in all tasks. So this is a relatively new project, and it has a less developed community and training materials compared to CUDA. And if for your tasks integration with NVIDIA profiles and debuggers is important, CUDA will be more interesting variant. And also, this can be hard to integrate Triton code with existing CUDA solutions. But I wanna repeat it again that for such task like FlashAttention, this is an amazing tool. It lets us to write code much faster. This is much easier to support this code, and it takes less time to start doing this, and it takes less amount of lines of code. So that's why I decided to use this. And now we're gonna to overview the key implementation features, and also we will compare my implementation with existing ones. So, and we will start looking at existing implementations of FlashAttention 2. There are three popular solutions from Dao AI Lab on CUDA and Triton, PyTorch on CUDA, and OpenAI on Triton. So this is very long to read, but I will tell you the main drawbacks. First of all of them support only Ampere Plus architecture, so that means that you cannot run this on Turing. The second lag that it has no any interface to write your personal CUDA kernels. The next drawback that optional determinism is available only in Tri Dao implementation in CUDA. Yes, you can get determinism using PyTorch implementation, but for this you need to apply synchronization, and there is no any place where it was described. So only after several experiments I understood how to do this. So another problem that Triton solutions, they work as a Triton only on Linux in a pure view, and also means that we need to use the custom Triton. So there is a such project like Triton Windows, and in my implementation, when you start installing this library, you can get the correct Triton version depending on the platform. And also there is one problem with Triton that starting with Triton versions 3.3 and higher has a bug which is linked with the increased shared memory consumption, and this is noticeable especially on all GPUs like Turing or Ampere. And to get the most let's say most enjoyable experience with FlashAttention, you need this legacy version of my implementation. How to do this we will look a little later. So also there is no any information that these implementations can work in heterogeneous environments. So it means if you have several GPUs, for example 800 and RTX 4060, that means that they won't work. So I watched the source code of these implementations, and there is no any appearance of code where this problem is solved. So in my implementation this is possible to do. So and now we need to start looking at my implementations. As I said before, my implementation works with Turing support. So it has a Turing support. It works with T4 or 2060 NVIDIA RTX, and there is one interesting fact that even on 1,000 tokens, the training speed up is significant. So it takes 135 seconds instead of 180 compared to vanilla attention. Also, in this implementation exists the customization of kernels. So that means that there is a manual mode when you can write your own CUDA kernels. So you can write, for example, block sizes or number of warps and other things. So also it supports determinism, and as I said before, it has a cross-platform support and heterogeneous GPU. Okay, how to use this? After you write pip install FlashAttention Triton, then you import from FlashAttention Triton FlashAttention v2. You insert QKV matrices, shape, batch, number of heads, cycline Q, and head dim. Then you need to point SM scale, but you can't do this. All depends on your tasks. And you can have a deterministic flag, so you write deterministic true. So, but more interesting mode is a FlashAttention v2 custom. So this is a custom mode, and it lets you write your own CUDA kernels. So how it looks like. So we have a Triton config for backward pass. So here we can point block sizes for Q rows or KV calls. Also, we can point sequence parallel mode. So if this is false, that means that we don't use atomic operations. So, but here below, we use this mode. So that's why this is called non-deterministic, because we use two settings, and one of them is non-deterministic. So here it said before we can write block sizes, min warps, max warps, num stages, and other things. So then this is added in a dictionary where key is compute capability of GPU. So for Turing this is 7.5. That's why it's written 7 and 5. And then you insert QKV with the same shape is as in the FlashAttention v2 mode, and you point this dictionary into kernel's configs parameter, and that's all. So now you can get a very cool thing. So this implementation has some pros, and you will never find this in existing implementations. So that's what I want to tell you about FlashAttention. And at the end, I want to tell you that this project was very hard for me. I mean, in terms of open source, this is the most cool and hardest open source project. And I'm glad that I did this because it solved the real problem, as I said before. And I decided to share this with people, and also I decided to write the normal tutorial because in my opinion FlashAttention is a very important topic because this is used widespread, and I decided to bring something fresh and more flexible. I hope this will be useful for you, and I'll be very pleased if I knew that my implementation was used in production code of some companies. Also, I want to express my special gratitude to Tri Dao and his team Triton team for a cool tool, because with this tool I wrote this implementation. And also I want to thank my brother Maxim, this is the Russian name, because he helped me too much in testing. So this is not the end. Next, in the next, I want to create a series of tutorials with ChatGPT from scratch. So this is the same structure with ML algorithms from scratch course, but only with ChatGPT. So it consists of a lot of components like tokenizer, like trainer, like GPT model, and for example, PPO algorithm. This is from RLHF. And I want to create a series of videos with papers in Russian and English on Haberkagel on YouTube and GitHub. And I hope that these tutorials will be useful for you. And after this, also I'd like to do the same things with Sora, and something which reminds AGI. So I mean, I also want to write it from scratch and to share with you. But when I do this, I don't know now, because I have also some businesses and projects, and after this I will come back to my plans. Also, I want to say that this is my first video, and I thought this would be more simpler to record such things, and I think that in the future my skills in this direction will be much better. But anyway, I hope that it was useful for you, and I can only wish you success. So good luck and see you soon again.